All right, so we're going to take a look at the thermodynamics problem set, and I am going to play the role of student and just illustrate for you how I would solve the problem. So let's take a look at the first one where we have the following equation, and so I'm going to go ahead and just write this the way that I normally would. Okay, here we are. So we have the following equation. We're looking at the combustion of methanol. So we have CH3OH that's in the liquid state. And we have 1.5 moles of oxygen gas, so that essentially is 3 oxygen atoms. And this yields 2 liquid water molecules. Plus 1 mole of gaseous carbon dioxide. So we can consider this to be a complete combustion, because when we combust a carbon compound, we should always get CO2 and H2O as our major products. We're additionally given information that the delta S for the reaction is minus 19.3 calories per mole Kelvin. Because this is in calories, this is a fairly old question. Really, in the current state of chemistry, we use joules rather than calories. But all of our data is going to be given to us in either calories or kcals. Notice we're also given information for the delta H of formation of all of our reactants and products with the exception of O2, and we know that O2 is an element in its standard state, and therefore its delta H of formation will be 0. But we know that the S of formation will be non-zero. Again, there's no energetic requirement for something that already exists, but there is some inherent energy dispersal that existing element has. So I've often referred in class, you can't make something the Lord's already made. However, something the Lord's already made already has an innate ability to disperse the energy which it possesses. So probably they're going to ask us to calculate the S of formation of O2 eventually. We also want to remember some mathematical functions. Delta G is equal to delta H minus T delta S. Let's take a look at some questions. Part A asks us to calculate the delta G for the combustion of methanol at 298 Kelvin. So we can find the delta H by using Hess's law. That means that the delta H of the reaction is going to be equal to 2 times the H of formation of H2O plus the H of formation of CO2 minus the H of formation of methanol. Again, there is no H of formation of O2 because it already exists. That is, its H of formation is equal to 0. So now I can just substitute these mathematical values. So for H2O, it is negative 68.3. So that will be 2 times negative 68.3 plus, for CO2, negative 94. Minus a minus will be plus. Notice these H of formations are always going to be exothermic because they're made from their standard elements, which will be 0, which means that all the bond forming processes will be exothermic. So it shouldn't surprise us that all of these delta H of formation values are negative. That actually is in line with what we know about bond making and bond breaking processes. So now all we need to do is to simplify this expression. And when we simplify this expression, we get a delta H of negative 173.6 kcals per mole because we are combusting 1 mole of methanol. So this is our delta H of the reaction. Now, we're given the delta S of the reaction, but we need to convert this for the purposes of applying the first form of Gibbs free energy. We can't add units unless they are like units, so we need to recompute the delta S as negative 0.0193 kcals per mole Kelvin. And of course, we'll be multiplying this by 298 Kelvin. So now applying Gibbs free energy equation, delta G is equal to minus 173.6. Now we're going to have a minus, so that's going to change that sign to a positive. 0.0193 times 298. So the unit here will be kcals per mole. The unit with delta H will be kcals per mole. I can now add those together. So delta G is minus 173 plus 0.0193 times 298. And this is negative 167.3. Actually, I'm going to round it down to 0.2. kcals per mole. And that answers part A. Notice we had to do quite a bit of calculating on part A because we had to find the delta H before we could find the delta G. So this is the solution to part A of the first FRQ on this problem set. We can now move on to part B. Calculate the value of the equilibrium constant. Now, when we were doing the thermodynamics problem set, I never required you to do this, but now that we're doing equilibrium in class, we know that delta G, which by the way is negative 167.2 kcals per mole, is equal to minus RT natural log of K. If I do exponential algebra to get rid of the natural log, first let's divide by minus RT. So we get delta G over minus RT. So I'm just going to bring out that minus sign. Is equal to the natural log of K. If I raise this equation to base E, the base E of the natural log is 1, and that side cancels to K. So K is equal to base E to the minus delta G over RT. Now R in gas law computations is 0.0821 liter atmospheres per mole Kelvin. When we're talking about energy, it's 8.3145 joules per mole Kelvin. And 1 calorie is 4.814 joules. So in terms of calories, which is what is relevant here, it's going to be 2 calories per mole Kelvin. Now that's a bit of an estimation. I think it is actually like 1.99. So rounding to 2 is just fine, and it makes the math a little bit easier if you're estimating. Now I have to convert delta G to joules. So it's going to be minus 167,200 calories. I think I said joules a minute ago. I meant calories. Calories per mole. And this is important because when I divide this by R, 2 calories per mole Kelvin times 298 Kelvin. When I do an exponential, I cannot have any units. Remember from class that K, big K, the equilibrium constant, is a dimensionless quantity. So the kelvins cancel in the numerator, and the calories per mole cancel in both the numerator and the denominator. So now all we have to do is plug and chug, and of course this will be what we take E to. And there's already a minus sign that's intrinsically here. So this will become a positive. Remember, a negative delta G should give a value of K that is greater than 1. In fact, significantly greater than 1. So really what we're evaluating is E to the 167,200 divided by 2 times 298. And when we simplify this expression, let's do this quickly. we get a value that our calculator can actually not handle. So the exponential that we get is going to be greater than 10 to the 100. Boy, it would be awesome to have that much money in my bank account. So 167,200 divided by 2 divided by 298 gives me e to the 280. This means I essentially have an irreversible reaction. It's not at equilibrium. The K constant is essentially approaching positive infinity. And so we never really worked these problems when we were doing thermo, but now you're expected to be able to do that. Finally, let's end this one with part C. Calculate the standard absolute entropy S for O2, which is what we thought they were going to ask us from the beginning. And so we can use Hess's law to accomplish this. We know Hess's law, delta S of the reaction is equal to 2 times the S of formation of H2O plus the S of formation of CO2 minus the S of formation of methanol. I'm just going to abbreviate that MEOH minus 3/2 times the S of formation of O2. And this is what we want to solve for. So I'm going to add this last term to both sides and then subtract the delta S of the reaction. So I'll get 3/2 S of formation of O2 is equal to, now, positive 19.3 plus 2 times 16.7, that will be 33.4, plus 51.1 minus 30.3. And then finally, I want to divide all of that by 1.5. So now again, it's just going to become a plug and chug type problem. We have 19.3 plus 33.4 plus 51.1 minus 30.3 divided by 1.5, and we get an answer of 49 calories per mole Kelvin. Now, we know from thermodynamic tables that in joules this should be 205. So if we multiply this by 4.184, we get 205.02. So our work checks out. So this answers the last part of FRQ number 1, which is 49 calories per mole Kelvin. So this is the complete solution to FRQ number 1. And in the interest of keeping these short, I think what I'm going to do is just do one of these FRQs at a time. So I'm going to stop this video at this point.